Thanks a lot. Okay, so we're going to talk about STL iterators today. And this is a way that we can access data in containers, those basic classes like lists and vectors and so on, in a standard way. Okay, so last tutorial we talked about two things. We talked about C++ templates and how we could use those to make functions that worked on a variety of data types, and also how we could use them to create class templates where we could make a class that could store and manipulate various types of data. And then we started looking at how those templates are used to build a powerful library in C++ called the standard template library. And we started looking at what's called the container classes. And in particular, we looked at standard vector, very useful container for data. It's basically a better array. So today we're going to go through in the first hour a few different things. First, what is an iterator? What operations can I perform in an iterator? And iterators basically are used to work with containers. I'm going to show you what they are in a few minutes, but they're very useful for working with these container classes like vector and list and so on. Now, we already talked about vector. We're going to talk about another container class in this first hour called list, and look at what is it good at and where we use it instead of a standard vector. And again, if you have any questions, type them in the chat or raise your hand so we can answer them right away. Okay, so what's an iterator? So an iterator identifies an element in a container. So it's a lot like a pointer. So I told you last week that with STL, you don't have to use pointers as much, which is true. We do use iterators, which provide an abstraction. They behave a lot like a pointer. They point at some element within a container. So why do we need that? They let us access an element in a container, which again is what we use pointers for. They allow us to move between elements in a pointer in a container. That's similar to pointer arithmetic. In C++ pointers, you can actually add 1 to them, you can increment them, you can add 4 to them. And that actually means incrementing them means point to the next element. Adding 4 to them means point to the element 4 later than what I'm pointing at right now. Iterators let us do very similar things. Iterators in C++ are restricted to efficient operations, or in the STL are restricted to efficient operations. So again, this is a choice that the designers of the STL made. If it can't be done quickly, they just don't define it, and therefore you get a compile time error if you try to use an iterator in a way that it actually doesn't work well. Rather than making that work but being really slow, they just don't define that operation for that iterator, and the compiler will say that doesn't exist, you can't compile that. Which is actually doing, I think, a good choice on their part, because instead of writing slow code, you just get a syntax error and you have to go fix it. Okay, so why do we need iterators? So for vectors, it's not as important, but it is going to be important for some other container classes. So for vectors, we saw that we could use this notation. We could use array. We could take an array and just use the subscript operator to access different elements, and we can do the same thing with vector. It also supports this square bracket or subscript operator. So for vectors, the truth is you don't have to use iterators that much if you don't want to. But this square bracket operator square bracket, implies random access, that I can efficiently get at entry 1, entry 20, entry 1 million if it exists in the vector or the array. Not all containers support random access. For example, lists do not support random access. So for those other containers, we need some other way to refer to where we are in the container to get a specific element. So in STL, all containers have iterators defined. And again, they're a generalization of a pointer. They allow us to say, what am I pointing at? Let's operate on that thing. Now, all of the iterators that the STL defines, you use the same member functions, but the actual types are different because these are templated types. So remember, a template is a recipe, but you get a specific kind of class when you invoke that recipe with a certain type. So for example, there is an iterator, and this : means it's the scope resolution operator. It means this name is inside some other namespace or group of names. So this says the iterator that goes with a vector of integers. This says the iterator that goes with a vector of floating point numbers. And this says the iterator that goes with a list of integers. All of those iterators are going to have basically, you're going to invoke their member functions in the same way. So you're going to find that once you know how to use one iterator, you pretty much know how to use them all. But you have to remember that each of them is actually a different type. You just can't set one iterator equal to another. If their types aren't the same, C++ will complain. Okay, so let's go back to standard vector, which we covered last week. So we've already covered a few operators. We looked at the square bracket operator, which we can use to access entries. And if we put it on the left side of an assignment, we can also use it to modify entries in the vector. We can grow our vector with the pushback member function, and we can ask how many elements are in the vector with the size member function. And all of these methods are fast. So they're all order 1 methods, constant time. Today, we're going to learn some new methods. We're going to learn the begin method. This returns an iterator to the first element in the vector. And it doesn't just work for vectors, it'll work for other container classes like list. And the end method. The end method returns an iterator to the element that's just after the last element in the container. So in this case, the vector. So we use this to see what are we done. If we're looping through a container, or again, a vector will be the first example we use here, we can use this end iterator to check when have I gone beyond the end of the container. What am I done? Okay, so where are begin and end? So let's say I have some vector. So I've declared an object named vector, or my vector. And if I call it size member function, it says I have n elements. So those n elements are going to be indexed from 0 to n minus 1. So begin is going to point, if I call my vector.begin, we're going to get an iterator. So again, it's like a pointer that points to the beginning, the first element of this my vector object. And if I call end, it's going to point 1 past the end. Okay, so it's not going to point at the last element, it's going to point 1 past the last element. And we're going to use that just to check if we're looping through the whole vector, we can use that to check have we hit the end yet. Okay, one thing we should not do, by the way, is we have to remember that there's nothing there. Okay, this is for checking, am I at the end? We should not ever try to access that because it's like accessing the array of n. There are entries from 0 to n minus 1. There's nothing at entry n. Okay, so I'm going to do it. There's a question, is begin a method we build or is it made by default? So it's made by default. So these methods exist. So for vectors, they've all been defined and you just call them, okay? So I'm going to do a quick poll because I want to get you guys to figure out which of these operations do you think are allowed. In other words, they'll compile. And if they compile, they do something reasonable. So we're going to invoke a poll right now where you are going to take your best shot, even though I haven't taught you all about iterators yet, at which of these are going to compile. So we've got 9 different lines here. And then we're going to go through what, for the ones that do compile, so they're allowed in C++, what does each one do? Okay, so how should you fill this out? Basically, an iterator is presenting the same abstraction as a pointer. So think about, would I be able to do this with a pointer? And does it make any sense? So if it doesn't make any sense, C++ won't let you do it. But if it does make sense, then it's a good heuristic is going to be then it's allowed. The one difference between a pointer and an iterator is that the iterator is intended to be used with just one container. So it's used with a certain vector, for example. You can use it to go through that vector. You can't just make an iterator point at some arbitrary piece of memory. You can do that with pointers. You can't do that kind of thing with an iterator. So with that information, why don't you try and guess which of these lines are going to compile? And this is not going to be not going to be able to guess this perfectly because you haven't yet learned the rules. So we're going to go through this. But it's a good idea to try to think about, well, can you guess what each of these things mean? It'll make it stick in your mind better if you take your own shot at it before we go through it. Okay, so I'm going to stop talking and let you just go through this for now. Yeah, I see Harshit saying some made to stick techniques being used here. So yeah, I'm trying to create a knowledge gap. Make you do it and guess what do you think would happen. Also trying to make it concrete instead of giving you abstract definitions of what an iterator is. Let's just try to say, does this make sense? Does that make sense for concrete examples? So thank you, Harshit. I was trying to use made to stick principles, and I'm glad you recognize that. Okay, so I'm going to give you like another maybe 40 seconds or so, and then we'll reveal the poll results and go through these. All right, so last 10 seconds to get your answer in, and then I'm going to end this. Okay, so let's go through. Let me show these results. Let's see what people said. Okay, so for the first line, and everything is starting with this. Okay, so what I've done here is I've declared a vector of integers and I've initialized it. I put 4 different entries in it. So it's going to have size 4, and that's what's going to be in index 0 through 3. Okay, so first line, 95% of the people said that it would compile. So we've got a standard vector of integers. We're saying give us the iterator that goes with that. We're going to name it IT, and we're going to set it equal to numbers, which is a vector of integers. And we're going to set it to be pointing at the beginning of that vector. And yeah, you're right, that works. So it's going to point at the start of that vector. We made a vector of the right type, or an iterator of the correct type, and we set it equal to the beginning of some vector. So that's going to work fine. Okay, next line. So iterator equals 5, and 76% of people said it wouldn't compile, 24% said it would compile, and yeah, that one won't compile. So 5 is an integer, it's not an iterator. You might think maybe that makes it point at the 5th element. It doesn't. You can't make an iterator just go to an arbitrary memory access like this. So with pointers, you actually can do things like this, but you can't do it with iterators. And it's not the right type. We can't set an iterator equal to an integer. Okay, so number 3 is IT++, and 85% of people said that should work. So what do you think it'll do? Type it in the chat if you got an idea of what that's going to do. Yeah, so move 1 to the right. That's exactly what it's going to do. So yeah, so we were pointing at the first elements of the vector before, so index 0. Now we're pointing at the next element, which is actually index 1. Okay, IT++ works, then IT minus minus is probably going to work. And let's see, that's what people said in the poll as well. So 78% of people said that that would work. It's actually a little bit lower than the 85%, but that is going to work. Okay, so IT minus minus is just the opposite. Makes the iterator point at the previous element. So we were pointing at the second element in the vector. Now we're back to pointing at the first element. Okay, so the next line is int x equals star IT. And 73% of people thought that would compile, and yeah, that will compile. So what do you think that does? Does anybody want to take a shot at what is that? If it was a pointer, what would that do? Because again, an iterator, it's a class, but it presents the abstraction of a pointer. Yeah, so it's dereferencing. So it's basically saying take the value that IT is pointing at, get that value, and set x equal to it. Okay, so IT is actually pointing right now there. So the value that it's going to get is 1. Okay. Let's see. So then the next one is IT not equal to numbers.end. Is that going to compile? And 78% of people said it would. And yeah, that will compile as well. So basically it's checking, is the iterator pointing at the end? So iterator pointing at the end means it's past the end of the vector. So it's not. The iterator is actually pointing there. So this would return that it's not equal to numbers.end. So it would return true. But that's what that line would be checking. Next line, IT less than numbers.end. And 66% of people thought that would compile. And yeah, it will check if it's not pointing at the end or it's before the end. And given where our iterator is right now, it's right there, and this is where end is, this would return true. Okay, the next one, star IT equals 27. 63% of people thought it would compile. Somebody who thinks that it would compile, what do you think it's going to do? So anybody have an idea of what this line is going to do? Star IT equals 27. So 63% of you thought it would compile. What do you think it's going to do? Yeah, change the value. So IT, let me erase this. IT is pointing at this entry. So after that line, that number would have changed to 27. Okay, and then the last line is IT equals numbers.begin plus 2. What's that going to do? So let's erase all this. First, 80% of you thought it would compile, and you're right, it will compile. Whoops. What will it do? So IT equals numbers.begin plus 2. Yeah, it's going to point to 3. So numbers.begin would be an iterator there. Okay, and I add 2 to it, it actually skips over 2 elements and is pointing there. So it would be pointing at 3. So that's exactly right. And this is basically the way, again, pointers work. So it's kind of C++ using made to stick principles. You already know how pointers work. So they're using an analogy to something concrete that you understand and saying iterators are like pointers. And now they're easier for you to understand how to work with. I see there's a question. Someone asked a question, would numbers.end be out of scope? Numbers.end would be in scope for all this code that I've written here because numbers is in scope. So if numbers is in scope, I can call this member function numbers.end. Okay, so any questions on that? You guys did well guessing, without me having shown you what the rules are. So you did a good job of guessing what the rules would be. There is a logic to how people make programming languages, so you can often guess the rules before you're taught them. Okay, so let's look at how we can use iterators. Let's see, there's a question here. If the first element was 5, okay, this element was 5, say, would case 7, this one, return true or false? Case 7 would still return true. The reason is it's checking the iterator. It's checking if the iterator, which was at that line in the code is pointing there, if that iterator is less than the end iterator. And so in other words, comes before it. And it does. It doesn't actually matter what's stored here, whether it's 1, 5, or 1,000,000. Okay? Okay, so let's look at how we can use this. So I'm going to loop through a vector. So we've already learned how to do this last week. Here's my little vector of integers. I've initialized it to have 4 elements, and I put 1, 2, 3, 4 in those 4 elements. We already know how to iterate through this using indices. So we did this last week. We just start index 0, keep going while we're less than the size, and we can print out every entry with the square bracket operator. We can do the same thing with iterators. So we have to get the right kind of iterator. Okay, so we're declaring an iterator object. It is an iterator for a vector of integers. So it's kind of a long type. Basically, if you actually looked inside the vector templated class, you'll see that it defines another type called iterator. So that's what we're accessing here. We set it equal to the beginning, or to point at the beginning of this vector. And then we go through this loop. Every time we go through the loop, we print out what we're pointing at. So we dereference it. So this is going to print out 1 the first time through, then it's going to print out, well, the next time we go through the loop, we basically are going to execute this. So we're going to increment the iterator. So our iterator is going to go from pointing at entry 1 to pointing at entry 2, and then we're going to print out 2. I'm going to keep doing that. We're going to do that 4 times. And finally, the last time through the loop, we were pointing here. We're going to increment. We're going to be pointing out there. That is actually where the end is. So the iterator is going to be equal to numbers.end. We're going to break out of the loop and come down here. It's going to print the exact same thing as what we printed with indices. Okay, it just says all the same things that I just talked about. Okay, so why would I use iterators in this case? Like, which code do you like better? Do you like the iterator code, or do you like the index code? Yeah, so almost everyone likes the index. Well, the first 2 people like the index. I like the index better too. So the truth is, with vectors, this is the code I'm going to write. I find that easier to read. Types are a little simpler. I don't have to work with pointers or iterators that are like pointers. So I would write this for vectors. Both are fine. They'll both be equally fast. But this index code is probably easier to use. Now, so you might go, well, why are we learning about iterators then? Why don't we just use indices? Vectors allow you to work with indices because they have this square bracket operator. Lots of other container classes like lists do not have the square bracket operator, so you have to work with iterators. So that's why we're learning it, but we're learning it with vectors where we actually have an alternative, and it's totally fine to use that alternative of indices. Okay, so let's go to a quick programming question. So I want you to extract the negative values of a vector. So this function with the meaningful name of extract negatives is passed a vector of integers, and it's passed it by references. And what I want you to do is create a new vector, and we've already declared it here. So we've got a local variable, which is also a vector of integers, and we're calling it negatives. How many entries are in negatives in this vector called negatives at this line? So after we hit that line, how many entries are in negatives? So you just have to look at it and go, okay, well, what's the size of that vector? Yeah, it's 0. Okay, so we use the default constructor of the vector, which does the logical thing. It creates a vector with no elements in it. So negative starts off empty. And what you're going to do is you're going to use iterators. You're going to loop over the integers vector, which is your input, and you're going to check every element. Is it negative? If it's negative, you're going to add it into this vector, negatives, and then at the end, you're going to return that negatives vector. Okay? So you could do this with indices, but we want you to instead do it with iterators to get some practice with that. Okay, so I'm going to put you into breakout rooms, and whoops. Don't look at that. So I'm going to put you into breakout rooms and give you a few minutes to try this. And same instructions as last time. It would be a good idea for you to turn on your camera if you're at all comfortable with that, so you can chat with your temporary teammate. Okay, so we're back in 4 minutes. And the link is in the chat, so you can just click on it. Okay, welcome back, everybody. Was that enough time? Why don't you type in the chat if you managed to complete it, or if you didn't manage to complete it. So you type yes for you did it, and no you didn't. Okay, so I see a few yeses and a few almosts. You can keep going. It's not a test, so if you're almost done, you can finish it off now. Okay, so let me show you the code that I wrote for this. So it's not very long. So I need to declare an iterator. So I'm going to call it IT. And the type is, again, it's an iterator, but the type of iterator that goes with a vector of integers, because that's what I'm going to be walking through. I'm going to start off by setting that iterator equal to integers.begin. So the start of this vector. So here's my vector integers. And I'm going to make my iterator IT point at the beginning. I'm going to go through until I get to the end, and I don't want to look at the end. So I keep going as long as I'm not at the end. And every time I go through the loop, I'm going to increment the iterator. In the body of the loop, I check what am I looking at. So I dereference the iterator to say what value am I looking at. If it is less than 0, then I want to add it into this other vector, negatives. And the way I create new elements in a vector is with pushback. So I call the pushback member function on negatives. And what I want to push back is whatever number was here. Maybe this number was -3. So what I want to pass to push back, the thing I want to stick inside negatives, is -3, what the iterator points at. So I dereference it. So after I've done this, negatives, after I've gone through this loop once, negatives would have size 1, and the one entry in it would be -3, if that's my example, where I put -3 in the first element of integers. Let's see, there's a question, instead of pushback, can you do negatives insert? Yeah, so we're going to see another member function called insert in just a couple slides, which allows you to put things not just at the end of a container, which is what pushback does, but to insert new elements anywhere in the container. And so if you look in the chat, you can see the syntax for that. And yes, I could have done that. And what is the difference between pushback and in place back? Maybe I'll talk about that. The difference is very subtle. I guess I can tell you quickly. You never have to use in place back. In place back means that the object basically, I actually have to go look at the details again. In place means that the entry already exists and you just want to construct something there. So you probably won't use in place back. It's a more minor function that can be used for efficiency if you know that you've already got an entry in the vector. So I guess the short answer is just use pushback, and place back is kind of a detailed one if you know the memory's already there and you just want to construct an object there. Okay, so maybe I'll go back one here again, sorry. Any questions about this? Does this make sense to everybody? Let me erase my scribbles. So if any questions, ask them now or move on. Okay, so I see at least one yes, so at least somebody's with me. So 2 people, great, thanks. Okay, so now we're going to erase the negative values of the vector. So we just took all the negative numbers, we put them in this negatives vector. I now want to get rid of the negative values. That's just the specification we're trying to beat. So we'll make a new function to do that. We're going to call it remove negatives. It doesn't return anything because it's just going to remove the negatives from the vector we pass in. So I'm going to pass in a vector of integers, passing it in by reference, which means we can actually modify this vector, and it will modify the variable that's actually passed in the calling function. What we're going to do is, again, we're going to iterate through the whole vector. So this is starting to look kind of similar. We declare an iterator of the proper type. We're going to call it it again, set it equal to the point at the beginning of our integers container, or integers vector. We're going to go through the whole vector. So we're going to keep going as long as the iterator is not at the end. We don't do any incrementing of the iterator here. Okay, so it's a little bit different for loop. What do? Well, if what we're pointing at is negative, then, so let's put in an example of our integers. So let's say this is integers. First time through, the iterator is pointing at the beginning. And let's say this entry was -3. So if the entry is negative, we call a new member function called erase. So we're going to call erase with an iterator. So we want to erase whatever entry we're pointing at. So this is going to be removed from integers. Integer size is going to get smaller, and we're not going to have that -3 in it anymore. And you notice there's kind of something interesting happen here. We also set the iterator equal to whatever this member function returns. The reason we do that is we just destroyed this entry. So what we're pointing at doesn't exist anymore. So we set the iterator equal to whatever is returned by this function, so it now points to the next entry in the vector or the container. So that's what we do. This whole if is what we do if it was negative. If it's not negative, so let's say we went through this loop and there was a 4 here, well, then we just skip over it. So that's easy. We just go iterator ++, and the iterator moves forward 1. So we erase that one, and now we're pointing at this new entry, which maybe has the number 6 in it. So it's a little bit more funky loop, but this is the way that you can erase elements from a container. So not just a vector, any container. So yeah, so Hershey has a question. So erase increments the iterator itself. Yeah, erase, it doesn't necessarily increment it. In this case, it is just pointing at the next thing. It does what, for a vector, it is just increment. For some other containers, it might have to do something different, but it always returns the iterator to the next valid element in the container. So it returns an iterator that you can use to keep going through a loop. Does that make sense? Question of, do we need the else statement? Won't the for loop increment it? No, I wrote this for loop in kind of a funny way. There's no increment here. So notice you're kind of used to a for loop that there's some kind of increment there. I don't have an increment there. It's empty. So there's no increment that happens. That's on purpose because basically we only want to increment sometimes. If we had a positive number, we want to increment to skip over it. If we have a negative number, we want to erase it, and we want to capture the new iterator that comes back from erase. So it's more complicated than just incrementing every time. So we don't put it in the loop control. We instead put it inside the body. Okay. Why can't you increment normally and erase as you go? It's not, it just basically will not work. Okay. If you increment normally, you are going to wind up skipping over some elements. So the way we have to handle the iterator here, where we're actually erasing elements, is more complex than when we're just going through and looking at elements. There are obviously many ways you can code things, but this would be like a pretty simple way to do it. And if I just put an increment in here, if I just said IT++, it's not going to work. Okay. For just reading the elements out, it would work. For erasing this, it wouldn't. Okay, so let's see. That just says what I told you. Yeah. Okay, so what does erase do? I just showed you this, but let's just show it again. So we're going through a vector, but it could be any container class. And our iterator is pointing at a certain element, say this one. We've already gone through all the elements before that because we're doing it in a loop, and there are some elements after it that we haven't gone through yet. We're pointing at this number, so if we want to get at this number, we would dereference the iterator. And let's say this number is negative. So we call erase on it, and basically that negative element is removed, it's destroyed. All of the ones after it are basically copied over. A vector can't have a gap in the middle. So these all have to be shifted over one, which actually is quite a lot of work. Inside vector, you don't do it, but inside the vector class, it's actually copying every single one of these elements over. And then it returns an iterator to the next element that you should look at, the next one that exists, which is right here. Okay, so erase did a reasonable amount of work. What happens to the element getting erased? So the element getting erased, its destructor is called. Now we have a vector of integers. The destructor for integers doesn't do anything. They're built-in type, there's no memory to clean up. If it was some complicated, if there were strings, for example, in our vector, the destructor for the string would be called. And then it's removed from the vector because all of the elements after it are copied over and the size is decremented. So you wind up with a vector that is one smaller than it was before with no gaps. And no, erase internally doesn't create a copy of the vector. Erase will just basically shift things over by copying elements. Basically index, you can think of this as indices. Maybe indices are easier for vectors. Say this was index 12. Okay, so index 12 I just destroyed. And I used to have size was 23. Okay, so the last element here was 22 was valid. Okay, and 23 wasn't. After I've destroyed it, all of these things get shifted over. What used to be an index 22 is now going to be an index 21. What used to be an index 13, so maybe this was the number 8, is now here. Okay, so everybody's index gets reduced by 1, and the size gets reduced by 1. So size here might have been 23, and size here is now 22. Okay. So, and actually Anthony has a good question. Is this the most efficient way of removing elements? For a vector it is. There's nothing else you can do. But what you've noticed is that for vectors, removing elements in the middle is not very efficient. Okay, so vectors are good at a lot of things. This is not one of them because removing an element requires a whole pile of copies. So inside vector, it's actually going through a loop and copying, moving everybody over by one, which is actually a lot of work. Okay. Yeah, and Dante's asking, is this the same reason there's no push front? And yeah, for a vector, there's no push front, and it's because it would be slow. You would have to put something in element 0 with push front, and you'd have to copy everybody else over. That would be doable, but slow. So vector doesn't let you do it because they prefer you get a compiler error rather than write slow code. Okay. Okay, so how does it perform? So it accepts, well, let's just talk about first what it does. So it accepts an iterator to the element should be erased. It returns an iterator to the next element in the vector, and its complexity is order n. The reason it's order n is because of this copy. This copy, in the worst case, could copy n elements over by 1, and in the average case, it actually does copy n over 2. So both the worst case and the average complexity is pretty bad. It's order n. So what's given that this is order n. Okay, so remember this, erase is order n for a vector. If I go back to, let's go back here. What's the overall complexity then of this routine, this erase negatives? So let's pause for a minute. Think about it, type it in the chat if you got it. So erase is order n. Yeah, so Dante's saying order n squared, Hannah's agreeing. Yeah, it's exactly right. So we've got a loop here that is going to go through n times, okay? And for every time we go through that loop, if it's negative, we call erase, which is also order n. Okay, so we get order, so the worst case is all negatives, in which case we get order n squared. So it's pretty bad, right? N squared is actually a pretty high number that we'd rather avoid. Okay, so can we do better? And you probably, if you looked at the next slide quickly as I clicked on it, you probably have an idea. So this seems kind of excessive. We just want to get rid of the negatives in a group of numbers, and we have an order n squared algorithm. So it's going to be okay if there are 10 numbers, but if there's a million, it's going to be a big problem. So what can we do to make this faster? And yeah, if you're quick at reading, you got an idea from the next slide. So if you got any ideas, just type them in the chat. What can we do to make this faster? And it's not a really complicated answer. So is vector a good choice? Vector is a good choice for a lot of things, but for this operation, vector is not a good choice because its erase is really slow. Yeah, and Dante's saying, well, use a list. And that is the best way to fix this. Because list has a fast erase operation. So part of what the STL is giving you is you can quickly create data structures, and they use the same member functions. So it's pretty easy if you know how to work with one container class from the STL to work with others. So you can just think about, well, what would be a good data structure for this, and just ask for it. So it's fast and allows you to write code that uses the right kind of data structure. Okay, so we've been talking about vector. That's the only container class you know so far. Let's talk about another one. So standard list, so std, because it's coming from the standard library, list, it's a doubly linked list. So just like you wrote in ECE 244. So we have some data. Data can be anything, okay, because it's templated. That's the data type that you're going to put in the angle brackets when you make a list. And then you never see these, but inside the list implementation, inside the recipe for list classes, it has a next pointer and has a previous pointer for every data element. And so that allows you to, easily, if you're pointing at a certain element, get to the next element. And easily, if you're pointing at a certain element, get to the previous element. It also allows you to have a fast erase and a fast insert. So the erase is fast because I can just, if I have an iterator pointing at this, I call erase. This is destroyed, so its destructor is called. And then to fix up the list is basically local operations. The next pointer of this just points there. The previous pointer of this just points there. That's all constant time. I called one destructor, I updated 2 pointers. So that was fast. That was erase. But insert in the middle of a list is also fast because it's the same idea. Create one object, put it in the list by changing a couple of pointers, and it's fast. Does that make sense? Is it clear why list has a fast erase? Okay, so I see at least one yeah. Give you a second to think about it if anyone has a question on it. And it's here you can see, well, why do I need iterators? Lists don't support indices. So the only way I could say erase this element is I need an iterator pointing at it. So that's why the erase member function doesn't take an index, it takes a pointer, because we want it to work with more than just vectors. In fact, vectors are pretty bad at erase. Lists are pretty good at erase. So we definitely want to make erase take iterators, not indices. Okay, so let's compare vector versus list. This is how you pick what data class you store things in. You look at a list of operations and you think, well, what am I going to use this for? So I want to use a class that gives me fast versions of the operations I'm going to use. So begin and end are order 1. Those are simple for both of them. Pushback is fast for both of them. Size is fast as well. So size is fast for a list because the list actually has an additional data member called size. If I walk through the whole, actually get rid of the brackets. So if I walk through the whole list counting things, it would be slow. To make it fast, the list stores a little bit of extra information. It actually knows how many elements are in it. Okay, vector's great strength is this square bracket operator, the index operator. It is not available for list. Okay, why do you think it's not available for list? So I kind of told you this, but why do you think it's not available? So could I, yeah, list doesn't have an index. List is not random access. So in theory, I could write a square bracket operator. I could basically make something, if I said, list of 2, that I would go, okay, well, that's 0, that's 1, that's 2, give me that. But in order to do that, I'd have to walk through the first 3 elements of the list. It would be an order n random access operator. And the creators of STL basically said that's not useful. I would give you a square bracket operator, and then our documentation should say you never ever should use this because it's really slow. So instead of doing that, they say, doesn't make sense. We will not write it because the only implementations would be slow and you shouldn't use them. Instead, you should use a vector if that's what you really need. By not making it available, if you try to use it, you'll get a compile time error with a list, and that's better. It's going to help you fix your code faster. Okay? So Shrina is asking, what about the size function? This size function was added in C++ 11, which you can use. The size function is, it's fast because of the fact that they added an extra data member. Oh, so you're asking, couldn't you use the size function for the indices? No, because the size member function is fast because they added 1 data member per list. So they decided that was okay. Makes the list a little bigger, but they make size fast. In order to make the square bracket operator fast, they basically have to add a vector inside the list because there's just no way to make that fast inside of a list. So, but that would become crazy. That would mean if you ask for a list, you internally also got a vector or something. So that wouldn't make sense. So that's why they don't do it. Okay, so erase is slow in a vector. Order n, and insert is slow in a vector. Insert at an arbitrary point in a vector is slow. And the reason is, here I was showing everything for erase, but the reason insert is slow is the same. If I was to add a new element here, okay, so if I want to say insert at some iterator, it's got to shift everybody over by 1 in order to make room. So it's slow for the same reason as erase was slow. That a vector, if you want to put something in or take something out, you have a ton of shifting to do to make sure there are no gaps. In a list, we already talked about why it's fast. You just put the new element in or take the old element out and you fix up a few pointers, so it's order 1. Okay, so let's see. Okay, and then the last thing is we talked about, we always use iterators. We can use iterators with any class, but we have to ask for the right kind of iterator. So we ask for a vector iterator with vectors, we ask for a list iterator with lists. Some iterators support only a subset of operations. So for vector, that's the most powerful kind of iterator. It's called random access. We can increment an iterator to move forward, we can decrement it to move backwards, and we can add 5 or add some number to just skip forward 5 elements. So IT plus 5 would skip us forward 5 elements. That can all be done with a vector efficiently. For a list, we have what's called a bi-directional iterator. We can increment it to go to the next thing, we can decrement it to go to the previous. We cannot do this. We cannot do IT plus 5. The reason is it's slow for the same reason. It would be slow for the same reason an operator square bracket is slow. We don't have random access, so you're not allowed to do this. If your code needs to do this kind of thing, then you should be using a vector. Okay? Does that make sense? So some types of iterators are essentially more restricted than others. It depends on what the underlying container can do. Okay, so what are these categories? So the most powerful iterators are called random access, and those are the ones that go with, for example, vectors and a few other data types. The next most powerful are bidirectional. Those go with list and a few other things like lists. And then there's something called forward, which is even less powerful. Forward basically lets you do IT++, but it does not let you do IT minus. And there's something called a forward list, which is, it has next pointers but no previous pointers. If you only ever want to go forward, that's going to save you a little bit of memory, so you could use it, but it means you can't use the go backwards iterator. Okay, so yeah, depending on what kind of iterator you have different operations allowed. So they all allow dereference, they all allow increment, but only some allow decrement, and only a smaller subset allow random access, where you can just skip forward 5 elements or 10 elements, etc. Okay, any questions on that? Does it all make sense? Okay, I'm going to take that as yes. Okay, so what do we have to do to replace standard vector with standard list? So our remove negative functions we just wrote was slow. Okay, this is the same function you wrote before, or I wrote before I went through. So there's nothing new here. If I want to replace this with list, so you notice I'm passing in a vector here, and I'm walking through that vector with an iterator, I'm erasing the negative elements. It was slow, it was order n squared. How do I turn this into list? Because we said list would be better. So what do I need to change? So just type it in the chat if you can think of what code you need to change. What lines, what needs to be done. Okay, standard vector, okay, needs to be changed. Yeah, so you're saying change from vector to list. And yeah, that's exactly right. It's actually, that's all you have to change. That's the beautiful thing about the STL, is because they use the same names for the member functions for all of the container classes. If I just change these vectors to list, it's fine. The code works perfectly. So it's pretty easy to change from one container class to another. So if you find, oh, I really wish I hadn't used this container class, I should do something else, it's not hard to change. Okay. And with list, remove negatives becomes order n. Right? We've got a loop here that we go through n times. But inside that loop, we only have constant time operators. Erase is now order 1. So this goes from an order n squared algorithms of vectors to order n with list. Okay. Let me show you another. We had questions last week about the auto keyword. So this is where auto now becomes useful. So instead of specifying a type like an int or an iterator, we can use the auto keyword. And when you type auto, it just means you're telling the compiler you should be able to figure out the type. So it can save you typing, and it can make it easier to keep your code compiling if you're switching around types, because you can change one type and some other lines can just automatically adapt, so you have fewer lines to type. You should always know what the type will be. So if you're using auto because you don't know what the type is, you should stop and think what's going on. The type still is static. The compiler is just figuring out, well, this could only be this type. It could only be an integer, or it could only be an iterator of a vector integer, but it still is figured out at compile time. It's as if you typed it, it never changes. C++ is called a statically typed language. Python, for example, is a dynamically typed language where types can change during runtime. In C++, types don't change during runtime. So the compiler figures it out, and it's as if you had typed the longer name or the longer type. So let's just see how we can use that. So this was our code to walk. Here's our code to walk through and print out the elements in a vector using iterators. And you wrote this a little while ago, so hopefully it looks familiar. The declaration of this iterator looks a bit long. Okay, iterator that goes with a vector of integers. And because this iterator, so we make an object called it, we immediately assign it the result of numbers.begin. And numbers, I haven't shown the declaration here, but it has to be a vector of type integer. So that's what it was. Because this member function returns an iterator for the container class. So if the container class was vector of integer, this must return an iterator for a vector of integer. So that means the compiler can figure out what type this has to be. So you can use the auto keyword here. Okay, you can use it because you're immediately assigning something to it. So the compiler can say, what is the type of what you're assigning? And that must be the type of the variable you want. So this can save you from typing some code. If you typed any other type here, it won't compile, because the compiler says, well, wait a sec, you immediately assigned this value to this iterator. If this type doesn't match what this returns, it's not going to compile. So in that case, you can say, well, in that case, I'm just going to use auto, because then the compiler should be able to figure it out, and I don't feel like typing so much. Let's see. Does that make sense? Okay, so if you have any questions, type in the chat. But yeah, auto can save you some typing. It's these iterators are a little bit of a long class or type definition, so this can be nice. Okay, let me quickly, okay, let's go on to my last slide. So I'm going to do a quick demo. So I said that vector is a lot faster. Let's see if this is alive. Good. Vector is a lot slower for this remove negatives function than list. So let's just take a look at a little example I've written here. Okay, so here's basically the code we were just looking at. So I'm defining n to be 1,000,000. So I've created a vector called v0 with 1,000,000 elements in it. And I fill that vector. I have a loop here that goes through the vector and just basically puts random data in it. So it fills that 1,000,000 elements with random numbers between -500,000 and +500,000. Then I remove the negatives. Okay, so I just walk through the vector. So I start at this beginning, keep going as long as I'm not at the end, and I do the code that we looked at in class, right? So if what the iterator is pointing to is negative, we erase it. Otherwise, we keep going. Okay, so this is a vector version of this. And let me bring up the. Okay, so this is a list version of exactly the same code. So the only thing that's changed is where on the left I have vector, on the right I have list. I make a list with 1,000,000 entries, fill it with random data, and then walk through and remove all the negatives. Okay, so I'm going to build these two programs, and we'll leave the vector version up. And when I'm going to compare speed. So when I do that, I should always use the release configuration. So I say make configuration equals release. Okay, so I already did this, so I'll just clean to get rid of it. Use the up arrows to go back. All right, so I just built two programs. One's called vec erase. Again, I can use the time command to time any program I want. So I'm running time on vec erase. So this is, again, 1,000,000 elements in a vector. Half are negative, half are positive. It's random, and I'm going through and removing all the negatives. So when I'm done, I should have a vector that's got around 500,000 elements in it, and they're only the positive ones, and they're in the same order they were in before. Okay, so this is still running. So while it's running, any questions from anybody? Okay, so it's order n squared. So we think order n squared can get slow. So how long did it take? It's right here. So this means 33 seconds and 65/100ths. So 33.65 seconds is how long that took, which is quite a while because all we're doing is removing 500,000 negative numbers. So that seems kind of excessive. How long do you think the list version will take? So the vector took a little over 33 seconds. So type in the chat if you got a guess. How long does it take? 2 picoseconds. Okay, so that's pretty fast. That's faster than the clock period of the computer, so that's unlikely. 3 seconds, 5 seconds, 3 milliseconds. Okay, so wide variation in answers. Okay, so let's type it. It's done. It took 50 milliseconds, so 0.05 seconds. Okay. So yeah, why did I do this? It shows the power of complexity analysis. If your program is too slow, the gains that you can get by changing your data structure, your algorithm to go from, say, n squared to n are enormous. They're far more than you're going to get by going in and trying to remove, micro-optimize your code and so on. This is already more than 600 times faster than the vector one. So yeah, you can't make up these kind of gaps by just trying to code a little more carefully. If you've got the wrong data structure, it's going to be slow. Think about that first. Okay, so let's take a break for, 5 minutes. So we'll start again at 10:18. And I'll be on the line in case you have any questions. And okay, so we're on a related topic, but now we're into other STL containers. So you know two, vector and list. We're now going to talk about a couple of other important ones. So the type of containers that we're going to be talking about in the next 40 minutes or so are called associative containers. And that's in contrast to vectors and lists, which are called sequential containers. You're going to learn about a couple different types of associative containers, ordered ones and unordered ones, and when to use each of those. Okay, that was all pretty abstract, so let's get into like more concrete examples. So let's motivate this. What are we trying to solve? So let's say we want to find a value in a vector. I'm not trying to find something by index. I'm actually trying to find a specific value. Okay, so let's say I've got a vector of strings and I'm looking for the value la in my strings. So you can do that without running very much code. So there's a function called, it's a templated function called standard find. It takes the iterator to, well, two iterators, and it'll search a container class between those two iterators for whatever you say you're looking for. So I basically said from the beginning of a vector to the end of that vector, I want you to look for this string, la, and this makes sense because my vector is of strings in this case, and return an iterator to that if you find it. If you don't find it, it's going to return end to indicate I didn't find it. Okay, so we can write it quickly. It has order and complexity. And the reason it has order and complexity is pretty obvious. In a vector, we have to go through every single element, and we have to check, is it this string? Is it equal to la? Okay, so yeah, start at the beginning until we get to the ending, go through and check every single entry, find if it's la. In this particular vector, that is the one that's la, so we would return that as found it. Okay, so return a pointer to that, or iterator to that. Okay, but that's pretty slow. Okay, so if we did that once, it's not a big deal. If we did it a lot in loops, it's going to be slow. So to make this faster, we could sort the container, and then we could use binary search to search it in logarithmic time. But that's going to be difficult and error prone. We're going to have to sort it. We're going to have to keep it sorted if we put new elements in and so on. So it's going to be a pain to code. Let's see. And yeah, Anthony's asking what happened if la was in here multiple times. It'll return a pointer to the first one. So it's just this find function is just returning one iterator. It'll find the first one and return it. Okay, so we can do better, right? If we use a vector without doing anything special, it's slow. If we sort it ourselves and write our own binary search, we're going to write a lot more code, and it's going to be error prone. So we don't want to do this. We want to use a data structure that is inherently ordered if we want to find things in it by value a lot. Okay, so how can we find something in a standard vector? And we don't want to find it by index. We want to find it by a certain value, or maybe I should actually change this. We should probably call that by key, okay? Because that's the more typical notation. We say we look up by key. So we could use standard find. But as I said, with a vector that's slow, so we want to use a better data structure. In ECE 244, you learned about binary search trees. How long does it take to find things in a binary search tree when you search by, the key? What's the complexity? Yeah, so it's log n. So a binary search tree is log n. And in STL, a binary search tree is called a map. So standard map is a binary search tree. So what are the benefits of using it? It's a self-balancing binary search tree. So did you guys, in your labs, did you write a binary search tree in 244 this year or not? Okay, so in many years, students write that, but I guess not this year. When you write it, you usually don't bother balancing. So a binary search tree is, if it's balanced, so it means that it has the fewest levels it can have, then it's a log n search, right? You'll only go through log n levels to find whatever you're looking for. Binary search trees can become unbalanced, like this, if your insert operator keeps putting things on one side, for example, and then they can actually get slow. The binary search tree in STL is good. It's what's called self-balancing, which means as you keep inserting elements in it, if the tree is becoming unbalanced, so it's starting to look like this, it will restructure it to make it balanced again. So it looks like, this. And this has fewer levels, so it is faster to search because every level implies one more comparison. So The binary search tree in the STL is fast. It guarantees log n, find, insert, and erase. Standard map uses a data structure that we wrote last week, the standard pair. So I told you pair was useful for combining a key and a value, and that's exactly how the binary search tree uses it. So the first data element is the key, the second data element is the value. So in a BST, the key is what you're sorting on, and the value is the data that's just coming along for the ride. Okay, so key is equivalent to the index in a vector. It's how am I going to access this? So a question from Lisa, how do you know when it restructures itself? You don't. So as you're inserting things or erasing things, you call those member functions, and then they basically, if they decide that the tree is getting unbalanced, they will do some extra work to rebalance it before they put the new entry in or remove a certain entry, and then they return. So it just happens. You don't do anything special. So I'm going to give you an example of using a binary search tree. That's a domain name lookup. So domain name lookups are part of what makes the internet work. So when you type in, I want to log into ug152.ecg.utoronto.ca, that's not how the internet actually works. The internet actually works with IP addresses. So 32-bit integers like this. And so this would be an IP address, just a 32-bit number. And normally it's actually shown 8 bits at a time. So you would see the number written like that. But that's actually an IP address, written 8 bits at a time with dots in between it. Difficult to remember those kinds of numbers. If we told you type that number to log into UG152, it's kind of a pain. So you can instead type in strings, and there are servers called domain name servers that map those strings to the appropriate numbers, and then that's actually the header, the IP address is put in your packet data to say go to this computer. So we're going to write a really simple domain name server. We need to have keys that are strings because that's what you want to type. Names like this UG one. The value, which is the data that we want to get back, is going to be an integer, 32-bit IP address. So what the binary search tree is going to store is a pair. Basically, every node in the binary search tree is a data type pair, and it's a specific kind of pair. It's a string for the key and an integer for the value. So hopefully you're with me so far. Type a question in if you're not. So let's see how to use that. Okay, so we have to include a new header file. So we include the map header file to get at this binary search tree. And the first thing I need to do is I need to declare my binary search tree. So I'm using a binary search tree, so a map, and I have to say what am I going to put in it. So I give it 2 types. I say I'm going to use a string for the key and an integer for the value, and then like any other variable, I give it a name. So I'm going to call it DNS lookup. How do I put stuff into this? I can make a pair. So I can say I'm going to declare a variable called Google. It's a pair of string and int, so key and value, and I'm going to use this constructor to initialize it, right? So google.com and that IP address, and then I can just put this in the binary search tree with this insert function, okay? So same insert member function that we talked about before, but with a binary search tree, it's going to be much more efficient than it was with a vector. That's the first way I can put things into my binary search tree. Here's an alternative syntax. So I could use my auto keyword, say I want to make an object called Apple, and there's a templated function called make pair that just takes 2 data items and makes a pair out of them. So I can say I want apple.com and this IP address. It'll make me a pair. It'll make it of the right type, so I can use auto. Okay, and then I can insert that. And then if I want the shortest syntax, I could get rid of this intermediate variable and just say, okay, insert in my binary search tree. I want to make a pair out of toronto.ca and this IP address. Stick that in. That'll be a new node in the binary search tree. All 3 of these things do the same thing. I'm just sort of gradually shortening the syntax, but they're all identical. Does it make sense? So this is how we can put entries into our binary search tree, which we're using for doing these domain name lookups. Okay, yeah, let me get rid of this. This is basically just saying the same thing that I talked about. Okay, so I've already put a bunch of things in, or I'm actually showing you the short form. So I basically am creating my binary search tree. It's initially empty. That's what the default constructor does. I put 3 values into it, and I'm using the short syntax to put them in. And now I want to go look things up. Okay, so I want to go find some names in here. Okay, for a binary search tree, the find function goes and looks for something in a container. That's what STL uses the member function find to do. So let me do a quick poll. What should I put in this brackets? So let me give you a few options here. Okay, so let me just give you 30 seconds or so to take a shot at this. So what should go into this? What's the input parameter into this find function? It's a key, a value, a pair of key and value, or just 5? Okay, so I'll give you another 20 seconds or so to just think about this. And then I'm going to close the poll. Okay, you've got about 5 seconds left, so take a shot at it. Okay, so let's see what people thought. So about 65% of you thought we should use a key. 14% thought we should use the value. 19% thought we should use both the key and value, put in a pair, and 2% thought we should just always use the number 5. It would be great if we could always just send the number 5 in and we could get the data we want. That would be a little too easy. If we passed in a pair of key and value, at that point we kind of know everything. We're saying we know both the key and the value, so there's not much to look up. So we don't need to do that. And so yeah, the right answer is the key. The key is what the binary search tree is sorted on. It's what can be efficiently located. The value is just the data that comes along for the ride. So in these examples, the key is the name. That's the way we define this. First thing is key. So key is the name, and that's what we're going to pass in. So we say, find me an iterator pointing to the data associated with apple.com. Give me an iterator pointing to the binary search tree node corresponding to Microsoft.com. So we pass in the key. All right, let me stop sharing this poll. So yeah, the key is like an index. So Harshit's asking, isn't the key like an index? And yeah, essentially the key is like a generalized form of index. In a vector, you have this nice index. It goes from 0 to 1 to 2 to whatever. In a binary search tree, basically the key can be anything, and we can look up by it. So it is like the index. What purpose does the value serve? So it depends on the application. It's basically, I want to store some data with this key. And there are cases where actually the key itself is enough. And you can do that if you want. So you can actually have empty values if you want. But more commonly, we have some data we want to go with the key. So in this example, we're actually trying to do domain name lookup, which means we are given a string, the string name of some computer or group of computers, and we get back an IP address. So our value is the IP address, this 32-bit integer. It's different in every case. So your value is, this is the data I would like to be able to look up. The key is, this is how I'm going to look it up quickly. Okay. Do real DNS servers use binary search trees? Yeah, they'll use a mix of binary search trees, and we're going to see unordered maps later. But this would be one of the key data structures that they would use. So, so the binary search trees and the sort of variations on that theme. Okay, so how do we check? So we're going to pass in the key. That's what we've done here. How do you think we check if the key was found? We get back an iterator. So it's like a pointer, points to a node in the binary search tree. How do you think, and it might not be there, right? Maybe we don't have any entry for apple.com. How should we check? What do you think? So if this was a pointer, we could check if it was null, right? That might be the check if it was a pointer to say we got failure. And yeah, I see already Srini and Dante are saying, well, check if it's not equal to end. And that's right. So we use the end value as essentially a sentinel value, meaning I didn't find it, something went wrong, it's not in the container. Okay, so if the iterator is not equal to our container was DNS lookup, that's the name of the container variable. So we say if the iterator is not equal to the .end value, well, that means that we found it. Okay, so you can think of end as being it's outside the container. We can check for it as if we're checking for a null pointer. And then we're going to print out a couple things. So the iterator points at an entire node in the map, and the node in a binary search tree has both the key, which is the first value in the pair, and it has the value, which is the second value. So we can say, use this iterator, print out the first value that it points at, use this iterator, point out the second value that it points at. First and second are just the members of pair, which we learned about last week. So this is going to print the key and value, okay? And so what we're going to get printed out is apple.com, and then this colon, and then the IP address. Is everybody familiar with this arrow notation? Do you know what it is? If you know what it is, type in what it is. So, okay, so people seem like it. Yeah, it accesses a member of a structure or a class, but instead of using dot, when you have a pointer to an object, you use dash instead of dot. So it basically dereferences and then selects that member variable. And the reason the names of the member variables that we're using are first and second is because a node in a map is actually a pair. And we already learned that a pair has both a first and a second data element. Okay, so Microsoft wasn't there. So we're checking if the iterator that comes back is equal to the end value, print out that we didn't find it. Okay, so in this case, we didn't find it, and that's what's going to be printed out. Okay, iterating over a standard map. So let's see, I'm going to put you quickly in breakout rooms. Here's my standard map. I've declared it. I put 3 values in it. I want you to use iterators and a for loop to print out all the nodes in the standard map. Okay, so I'm going to quickly put you in breakout rooms and try to do that in the next 4 minutes or so. Iterators for binary search trees look like iterators for vectors. So you already know how to work with these iterators. So you should be able to infer how to code this, even though you haven't done it before. Okay, so let me make a breakout room. Okay, welcome back, everybody. Let's see, did you have enough time to finish it? Just type yes or no so I get a sense of whether you managed to finish it on. Okay, so it looks like it was close. Okay, so looks not bad. There was a question in the chat just that I saw just as you went into the breakout rooms of what traversal does it matter? The traversal that you'll get is always in order when you walk through a map in STL using iterators. You will get an in order traversal. Okay, so let's look at how we do this. So yeah, the code's not too long. So I'm using the auto keyword here to shorten the code again. I need an iterator. I'm going to set it equal to the beginning of the point at the beginning of my binary search tree, DNS lookup. As long as I haven't hit the end, I'm going to keep going, and I'm just going to increment every time. I'm going to iterate to point at the next element. At every element, the iterator points at an entire pair, which is the key and the value. So I print out the first element, which is the key, and the second element in that node, which is the value. And yeah, they're going to come out like this. So they come out, notice that they didn't come out in the order I put them in. I put in Google first, then Apple, then Toronto. They come out Apple, Google, Toronto. So it's probably maybe it's obvious from what I just said, but why did they come out in this order? Apple, Google, and Toronto, rather than the order in which I put them in. Yeah, they come out sorted. So a binary search tree is fundamentally a sorting structure. That's why we're using it. It sorts on the keys. The keys are these strings that I sent in, and it will sort using operator less than. So operator, I guess, operator less than, which for strings is just alphabetical order. So they come out sorted in alphabetical order. Okay, so does it make sense? Any questions on that? So you didn't have the, I have to do that too. Harshit says he had to recite the whole alphabet, and I have to do that too a lot. As I said, many years in 244, you actually code this in the lab, and what you'll find is it's a reasonable amount of code. There's a lot of pointer manipulation, a lot of code to put in, make the inserts and the deletes and so on. To just ask for a binary search tree is one line in STL, and then you can just start working with it. So it is far more productive to just ask for a binary search tree rather than going off and coding it by hand. There's a question, will it do level order? No, it doesn't do level order. It basically walks up and down the tree in order to print it out in sorted order. So this plus plus is doing whatever it needs to do to get to the next node in the tree. And because the iterator is actually a class, it has code behind it that you don't have to go look at, but it's all there. So it makes sure that when we're doing this plus plus operation, we're actually walking through this tree. So we might have a tree that looks like this, and we would have started here, and then gone here, and then gone here, and then gone here, and so on, right? We'll walk through the whole tree in the right order. It's all done for you. You don't care. You just say, go to the next element in the tree, and because it's a sorted structure, that will always be the next element in sorted order. Okay? So the question, can I only insert pairs in map? Yeah, maps fundamentally want a pair. Can be a pair of anything. So the first type can be anything, the second type can be anything, but it's going to be a pair. Okay, let's look at what happens if you have duplicate keys. So I'm making a new map. It still has a string as its key. It has float now as its value, and it's a salary database. So I'm inserting things into it with keys of people's names and values of their salary. So I put 4 people into this salary database, and it turns out at my company, who would have thought it, but even with only 4 employees, I have 2 John Smiths, and they make significantly different amounts of money. So I insert all 4 of these in the database, and then I say, find me the entry for John Smith, and then I want to print out the first thing, which is the key. So that'll be the name, and then the second thing, which is the value. So that's going to be the salary. So what do you think this is going to print out? Which John Smith is it going to find? There are two of them. Yeah, so it's basically not going to insert the second one. So in a STL map, if the key already exists, the second insertion won't happen. Okay, so this John Smith doesn't really exist. And you're just going to, when you do this find, you're going to find the only John Smith you put in, 45,000. Okay, so in some cases, this is exactly what you want. You might not want duplicates to go in the binary search tree, but in some cases, you might want all of the duplicates to go in. In this salary database, I'd actually like all the duplicates. So there's another version of a binary search tree in the STL called multi-map. It works just like a map, but it allows duplicate keys. So all I have to do is change from asking for a map to asking for a multi-map. Okay, now if I run this code again, I'm going to wind up putting both of these in. Both inserts will happen because this data structure allows duplicate keys. And now I say, okay, find me John Smith and print out the salary. It's going to only return one of the entries though. Okay, so both of these entries for John Smith are in the tree now, but I said just find me an entry, any entry for John Smith. So I'm going to get one. Okay, I'll get an iterator pointing at that node, and I can print out the salary, but it's going to be one or the other. I don't know which one I'm going to get, but I'm not going to get them both. So let's see, there's a question from Anthony of would inserting a duplicate key give a warning? No. So trying to insert a duplicate key in a map, you won't get a warning. It'll just silently fail. It does return a data structure, so you can check if the insert succeeded or not. But if you know you're going to have duplicate keys, it's normally easier to just switch to a multi-map. And there's another question, is this still a binary search tree? Yeah, it's still a binary search tree. It's just a binary search tree with more nodes. Okay, so we could have two nodes with key of John Smith. Sorry, my text is not very good. We have two nodes with the same key. Still sorted. They'll be right beside each other in the tree. They're just allowed to have two nodes or more than two nodes with the same key now. So again, you have to decide, well, which flavor do you want? Would you like to have duplicate keys or would you not like to have duplicate keys? Depends on your application. Okay, so we got two John Smiths in here, but when we actually went to find John Smith, we're only going to get an iterator to one of the two. So there are more member functions. And the way you find these member functions is, I'll show you some references at the end of the lecture. But one good reference is c++.com. And for every container class inside of the STL, it tells you here are all the member functions and how they work. So there is a member function called equal range. And equal range is like a more powerful version of find. If you think there might be multiple matches and you want all those matches, then you can call equal range, and it actually returns a pair of iterators. So now you're not just getting one iterator, you're getting two iterators that give you the start and end range of all of the entries that match the key you pass in. Okay, so if I instead of calling find, I call equal range, and I say I want basically all the entries that match key John Smith, I will get back an iterator. And I'm just using auto because the type's going to look kind of messy. And the first entry is the start, with the first pointer to a node that matches this. And until I get to the second entry, I can keep going through. I've still got more nodes to look at. And every one of those nodes I can print out using the same syntax as I had before. Print out the key that I'm pointing to, print out the value that I'm pointing to. So the syntax of this probably looks a little alien at first. This is why you go to places like c++reference.com to see, well, how do I use this? I guess I'm just exposing you to the fact that there are other member functions than find. So if you need to look up a bunch of values, go look there. Okay. There's a question of, are they sorted based on keys and not values? Yeah, binary search trees, maps, they're always sorted on the keys. The values are just coming along for the ride. And then you're asking, why is it IT not equal to range.second? So basically, we have a bunch of iterators that we're going through now. Because we can have multiple matches, we actually have this IT, which is an iterator pointing at our binary search tree. So it's going to gradually point at nodes in our binary search tree. But because we have multiple nodes that might match, we actually have to go through this range. We start at the beginning of the range, and as long as we're not at the end of the range, we keep updating this iterator. So it'll basically initially point at the first thing, then it'll point at the second node, and then it'll point at the third node if there were 3 matches. Does that make sense? The syntax for this one gets a little more funky. So this is partly why you look things up, again, on websites like c++.com to see, how do I use this exactly? Okay, if I did this, I would get now both John Smiths printed out. So one John Smith earns $30,000 and another John Smith earns $45,000. Okay? So that's how you use a map, and a multi-map is a variation on that. Let me quickly summarize a bunch of very closely related data structures here. So we just talked about a map, which is a binary search tree. Find, insert, and erase are all login, which hopefully you remember from ECE 244. Multi-map is the same. It just allows duplicate keys. So it's still a binary search tree. It has the same find, insert, and erase complexity. Unordered map is, well, actually, let's do set first. Set is another binary search tree, but it's basically if you only need the keys. So if you have no values, the keys are enough, then you can use a set. It's just a binary search tree where the values are empty. And sometimes that's useful. Unordered map is even faster for find, insert, and erase. Instead of log in, it's order 1 for all of those things. It's not ordered. What do you think this is? So from 244, what data structure do you think that an unordered map is? Yeah, so an unordered map is a hash table. Even faster than a binary search tree for looking things up, but it's not ordered. So if you need it to be ordered, don't use it. If you don't need it to be ordered, it's usually, well, it is generally faster than a map. The way that you use it looks, basically all the code that I showed you for map, it's going to look the same if you use an unordered map. So that's, again, a nice thing about STL is to go from a binary search tree to a hash table. You pretty much already know the syntax to do it. There are a few other ones that you might choose to use later in the course. I'm not going to talk about them, but basically there are more data structures inside the STL. They're not as important, but there are queues and stacks and priority queues and so on. I'm not going to talk about these other elements, but basically you go to, again, a reference like c++.com, and it'll tell you about all of these things. These are the more important data structures up here, though. Okay, so let me just show you quickly a little bit about unordered map. So we talked about maps, and I just mentioned unordered map, but it's another important data structure. So both of them store key value pairs, and the code to work with them looks basically the same, right? The code that I showed you before, if I went and changed it from map to unordered map, I wouldn't really have to change anything else. So map is a binary search tree. So it looks like what I've shown you here. And it's order log in to find an element by key. It's sorted. Here I'm just labeling the nodes. I should probably actually put this in alphabetical order. So don't think of these as strings, just think of them as labels. And to use the standard map of some type, so if you want to put something in a standard map, that type, that key type, must define operator less than. Okay, so that's the key, that's the rule to use map. You have to give a sorting operator somehow, and the common way to do it is just that whatever you use as your key, so let's change this from type to just key, because it's the key type that has to define operator less than. Okay, you can also pass a comparison function if you want, but normally what people do is just the key type. If it defines operator less than, you can use it. So integers, strings, all these things, they already have operator less than defined, so you can use them as keys without doing anything extra. Unordered map is a hash table, even faster. It's order one defined an element by its key. It's not sorted, so if you need sorting, it's not a good choice. But if you don't need sorting, it's even faster. You can use an unordered map, and again, this is the key type, so I should really say key, as long as the hash function for it is defined. So does anybody know what does the hash function do? Again, you should have studied this in 244. So what is a hash function doing? I'll tell you if you don't know, but just seeing if anybody knows. Yes, the hash function is how we decide where to put the keys in the table. It basically takes from some key, so the key could be a string, an int, an object, whatever you want. It basically has to get essentially an integer, okay? So, and that integer is how it's going to decide to put it inside the hash table. For things like strings, integers, the built-in types and the common data types in STL, this hash function is already defined. Okay, so if you use any of those things as your key, it's just going to work. If you use some object that you made, so my fun object, and you want to use that as a key, you can, but you'll have to define this hash function. And again, you can see syntax examples of how to do that online. If you wanted to put your object, my fun object type, in a binary search tree, you would make sure that you defined operator less than. So these behave very similarly. Each of them requires one function to be defined. That function is different. Okay, so that is it for the tutorial. I'm going to give you a quick demonstration, and I'll hang out online to answer any questions you might have. Okay, so let's get into this. Oh, that's not what I want, sorry. Okay, so this is a little piece of code that creates a map, so a binary search tree. And this binary search tree uses a key that is an integer and a value that is an integer. This n is 1,000,000. So I basically insert 1,000,000 elements in my binary search tree. And the keys are just a certain integer, 2 times the index, and I basically create a bunch of random keys and a bunch of random values. I don't really care about what the keys and values are, so I stick a 1,000,000 key value pairs into my binary search tree, and then I'm going to go search for things. So I now do 10,000,000 searches, and I generate random keys. A third of them are negative, and I won't find those in the binary search tree because I didn't actually put any negative keys in, and 2/3 of them are positive, and I'll find those ones. Okay, so I do a find operation to say find this key, and in real code I would go do something with that, but I didn't bother doing anything. Okay, so that is put 1,000,000 things in a binary search tree and then do 10,000,000 random searches, 1/3 of which won't find it and 2/3 of which will find it. Okay, the code on the right is exactly the same. The only thing I've changed is if you'll see this line, I've declared a variable of type unordered map. It's got a key of integers and values of integers. Otherwise, everything else is the same. So again, map and unordered map, the way you work with them basically looks the same. I didn't have to change any of the code here. Okay, so why did I put all this code in? I want to test its speed. So if I'm going to do a speed test, I should always use the release configuration. So I get compiler optimizations and I can trust the results. Okay, which one do you think is going to be faster? So binary search tree or hash table. So map or unordered map. Okay, so I see people saying hash. Okay, so it looks like hash has it. Let's see, map search. Okay, so I'm using the time function again. Okay, so the time for a binary search tree was 0.86 seconds. So not too long, a little less than a second. Let's do an unordered map. And the time for that was 0.29 seconds. So yeah, so everybody who said hash table will be faster, it is faster. It's not the same magnitude of difference as we had between vector and list. So when we looked at something that was order n versus order n squared, the difference was enormous, factors of hundreds. And here the factor is 3, because the difference between log n and order 1 is not nearly as big. But still, the unordered map does have a 3x advantage, so it's a better choice if you don't need sorting. Sometimes you do need sorting, so if you need sorting, then use map. Okay, so that's it for what I had today. I'll hang around in case anybody has any questions. Let's see. So the question is, standard map and AVL tree or red-black tree? It's not defined by the standard library. So for those who don't know it, these are 2 types of binary search tree implementations that guarantee that the tree remains fairly balanced. So fairly balanced meaning so that we'll get logarithmic access all the time. If the tree becomes very unbalanced, so it has many levels, it can get slower. The standard library doesn't define which of those 2 you're going to use or anything. It just says it will be log n, which means you have to keep it basically balanced. Most implementations, I believe, use a red-black tree, but it's up to the library creator. And you'd have to do like searches to see what is the best known implementations. They're generally going to be using whatever is known to be the best, which usually is red-black, but there may be even fancier things nowadays. Okay, so let me go back to the equal range slide. There's a request for that. And let's see. Let's do this. Okay. Why don't we always use a hash table if it's all of its operations are order 1? Usually it's because of sorting. So if we looked at like the find function, and the find function works fine with either a map or an unordered map. There are some other member functions that will say, well, give me everything that's in a certain range, all the keys from this to this. Okay, and you can do that with a binary search tree, and you can't do that with a hash table. And sometimes that's useful. So there are cases where the sorting properties of a map are useful. Yeah, so a good default is use unordered map. If you don't know why, if it seems like both could work, then just use an unordered map because it's going to be faster. But if you go to c++.com, you're going to see that there are member functions other than find. And yeah, the ones that, for example, say find me everything from this key to that key. I want to find everything from Bob to Cobb. That there are member functions that will do that for a binary search tree because that makes sense. It's sorted. You can get everything in a sorted range. You can't do that with an unordered map. So that would be one example where a map is a good choice. And let's see. Someone asked me to go back to this slide. The syntax of this slide is kind of funky. So I mean, it's because you're essentially getting a range, which already is essentially iterate. This is like a pointer to a pointer in a sense. You're getting like a range, which is basically a begin and end iterator, and then you're going through that, and everything in it is in itself an iterator. So it's like a double pointer. So that's why maybe this code here, you go, that seems like it's a bit harder to understand. It is actually a bit harder to understand, just like double pointers are harder to understand. There was another question I saw, which is like, well, how can you have duplicate keys in a binary search tree? It's just the implementation. You would just basically say insert we'll keep the tree sorted. And if there was already, a key that had the name John Smith, then you don't stop your insert because of that. You just say, okay, I'm in the right part of the tree, figure out whether you should make a left child, right child, etc., and make me another node that's called John Smith that has key John Smith, but it might have a different value. So that's why it's useful to put it in, even though there's one already there, you can put another one in. So there are definitely cases where putting duplicates in is useful. It's actually not a huge amount of difference in the implementation of the binary search tree. It's just sort of details of exactly what do you do in insert and what exactly do you do in erase. I guess particularly insert. But you don't really have to worry about that because the standard library developers already did it. So whatever changes had to happen in insert, they already did it. Let's see. And let's see. So I guess your question, there's a follow-up question on that. Like, how do we know to go left or right if it's a duplicate? It doesn't matter. You just do either one, right? So if this was called John Smith, and you have to put another node in John Smith, you're saying, well, should I put it on the left or the right? Doesn't matter. Do either one, because it still satisfies all the properties of a binary search tree if you do either one of those things. Okay. Let's see. Since a binary search, actually, I'm going to stop the recording just in case people listening later don't want to hear all this.